Today we will discuss about Goodrick method of flood routing. As you know, flood routing is a method where we predict the hydrograph of outflow with the help of the hydrograph of inflow to a reservoir or channel or any other water bodies where flow of water is possible. So, how to predict the outflow hydrograph from inflow hydrograph, that is known as flood routing. And there are various types of flood routing like hydrologic flood routing, hydraulic flood routing. So Goodrich method of flood routing is an example of hydrologic flood routing, and it is mainly used for reservoir routing. That means from the inflow hydrograph to a reservoir, we try to predict the outflow hydrograph. And these inflow are due to some flood only, because that is why it is known as flood routing. Flood means for a very short time, heavy amount of rainfall has occurred in the upstream, so that excess amount of water will flow through the downstream. So with the help of the data of upstream, we want to predict the data of the downstream. So if there is a reservoir, that is the controlled river it is, then we use reservoir routing methods, and if it is not that, then we use another types of routing method. So Goodrick method of flood routing is an example of flood routing, and it is also an example of level pool routing. It comes under the level pool routing. And I have already discussed about modified pulse routing in my earlier video. And this is another example of level pool routing, which is known as Goodrich method of flood routing, and this is level pool routing is an example of hydrologic routing, and also it is an example of reservoir routing. Don't get confused among all these terms. So just remember, under hydrologic routing there is reservoir routing and also channel routing, and under reservoir routing we mainly use level pool routing, and under level pool routing we have modified pulse and also Goodrich method of flood routing. So let us see how this Goodrich method of flood routing is executed. So here the problem is that, let us see the problem. This is a working example. So the problem is you will be given storage, water level and discharge of any reservoir. Okay, so there will be a table given to you where storage, corresponding water level or elevation, and discharge or outflow will be given. Storage is represented by this S letter, and elevation is represented by the letter small h, and discharge is represented by Q. You see discharge is also here, discharge here can also be referred as outflow. And there is a term T. T is the time period, indicates time, and del T is the incremental time period. Okay, and there are two subscripts used here, 1 and 2. 1 indicates the initial time, 2 indicates the finishing time for the final time. So if I say Q1 is the outflow from the reservoir at the beginning of the time of the flood. Q2 is the final time or outflow at the final time of the flood. So 1 is representing the initial time, 2 is representing the final time or finishing time. Similarly, I is referred as inflow, and I1 is the inflow at the beginning of time scale or time period, and I2 is the end of time period. So if there is a data where time versus discharge is given in this manner, suppose time is 0, 6, 12, 18, and Q is at 0. This 0 can be hour, this 0 can be second, this 0 can be minute, anything it can happen. So let us say this is hour. So at 0th hour, the beginning of the time period, suppose the discharge was around 15 cubic meter. So after 6 hours, this is the end of first time period, it becomes 25. That is, the flood has come. Then after 6 hours, that is the 12th hour, it become 100. Then after 18th hour, this become at 150. Then after 24 hours, it starts to reduce 100. Then 30, 50. Then 36, then 20. Then I will say 42, 10, and after 48 hours, that is 2 days, the flood get diminished. So if I take this entire time scale from 0 to 48 as a single time period, then you will say 1 indicates the 0th hour and 2 indicates, this 1 indicates the 0th hour, 2 indicates the 48th hour, because this is the finish of the time period. Now if I consider this 0 to 6 as time period, then 0 will be the first, that is 1, and 6 will be the second, that means 2. Right? So always remember this, in case of flood routing, 1 in subscript means initial time, 2 in subscript means final time. So let us come back to our problem. So you will have a table where it will be given the storage in a reservoir, storage of water, or I will say water stored in a reservoir, and its corresponding water level and its corresponding discharge or outflow. So there will be a table where the storage is there. So I have said storage is represented by S, the letter S, and then you have this water level indicated by letter small h, and discharge is indicated by Q. So for some X amount of storage, the elevation is Y and the outflow is Z. So similarly, there will be data will be given, so sorry, this is 1, this is 1, this is 1, this is 2, this is 2, this is 2, then this is 3, this is 3, this is 3, and so on up to Xn, Yn, Zn. So this rate at when the storage in the reservoir is X1, the water level is Y1, and if the gates are opened, the gates of the reservoirs are opened at that time, then a Z1 amount of discharge will take place as outflow. Okay? So next there will be flood data is given at 6 hour interval. Yes, this is what it will be given. 6 hour interval. Suppose in the upstream there is a rainfall starts, and for that rainfall discharge will take place. So this is the discharge with respect to time that will be provided to you, and this will be actually the inflow hydrograph of the flood. This is the inflow hydrograph of the flood. That means suppose at some time suddenly a large amount of rainfall takes place within a short amount of time. So within 48 hours, that rainfall will create some discharge or runoff, which will come into the channel as discharge, and that discharge will flow through the channel and enter into the reservoir. So when it enters into the reservoir, that is your zeroth hour, and when it until 48 hours constantly inflow take place due to that rainfall through the inlet. So up to 48 hours it is recorded, and after then we have no change in discharge. So it is assumed that due to that rainfall discharge, the resultant discharge has already entered the reservoir. So this is your inflow hydrograph. Now you have to predict how much amount of water is there in this same time period of 0 to 48, which will be released if we open the sluice gate of a reservoir. Okay, that is the problem. And here say you see this T is equal to 0, as I have said, when that excess discharge, discharge due to that excess rainfall enters the reservoir, that is your T is equal to 0. So at that initial condition also, what they will give is elevation will be given. Elevation H. So now they will ask that find the flood hydrograph at the outlet. Outlet means at the reservoir outlet, with the help of Goodrich method. That means you need to find out the outflow hydrograph. So what will be the first step? First step will be to draw a discharge versus water level or elevation curve from the data given at point A. So this table, from this table, you have to draw a curve where in the y-axis you will put the discharge or outflow, and in the x-axis you will put the elevation. So that is what you have done here. And how we will do it? So you have this data table: storage, elevation, Q. Please remember, elevation is water level is elevation in case of reservoir. So you have that data, and what you will do straight away, you have to draw a graph of discharge versus elevation. So this Q will be your y-axis, this elevation will be your x-axis. Correct? In the second step, what will happen? You have to draw a storage discharge versus elevation graph from the data given at point A in the same as one. So here X is your elevation. What is Y? Y is this term. This is your RHS of this equation. I will come to this equation later on. So this RHS, right hand side of this equation C, this will be your Y. 2H2 by del T plus Q2. H2 is the storage and Q2 is the outflow, and del T is the time period. This is 0 to 6 is the time period, time increment basically. I have already said about del T, discussed about that. Right, so 0 to 6 hour, 6 hour in this case is the time period. So del T is there, right? So everything you have, so you can easily find out 2H2 by del T plus Q2. Okay, and in this case Q2 will be the discharge at the final time. That is, what is the discharge at the 6th hour? What is the discharge at the 12th hour? So in this case, for the first time period, Q2 will be 25 according to this data, right? So for this Q2, how much amount of S is there? From this table you can easily draw how much amount of discharge is here. So initially, when you want to calculate 2H2 by del T plus Q2, you will use the data of this table only, not the data of this plot. This table is not required. While calculating this, 2H2 by del T plus Q2 means 2H2, 2 into x1 plus divided by del T. Del T is, you can take 6 hours as it is the incremental time given here for this problem. So del T is 6 hours, H2 will be given from this, Q2 you have to take the corresponding discharge, and then you have to calculate what is 2H2 by del T plus Q2. So don't take the data from this flood hydrograph, which is given at point B. Flood data is given at 6 hour interval. Just consider this 6 hour interval as the del T. Del T is 6 hours, it will be converted into second. So 6 hours into 60 into 60. So that will be your del T. And then you will use the H2 as this S and Q2 as this Q, not this Q. Okay, because you see, you do not know what is the storage here from this flood hydrograph. So you have to depend upon this initial storage, discharge and outflow, storage, elevation and outflow data given in the point A, right? So this point A will give you this first two graph. One is outflow versus elevation, and second is this RHS of equation C versus elevation. As the elevation is the common axis here, you can draw that graph in the same graph. So let me see whether I can see. Yeah, this is that. So this is your elevation in the x-axis, as you know, x-axis is common, and this is your y-axis where your outflow and RHS of equation C is shown. So this is your graph of outflow versus elevation derived from that tabular data of storage, elevation and discharge given in the point A, mind it. And this is your that 2S2 del by del T plus Q2. That means RHS of equation C data. But although there is H2 or Q2, all this thing is there, but you will take only the storage and Q from this table and the time increment of that flood data. Only that time increment will be taken from the flood hydrograph data, and you will use those data to find out the RHS of equation C, 2H2y del T plus Q2. Right? So note that in x-axis is common here. Y is outflow, y is RHS. So so let me tell this. This is our goal. The output hydrograph. We have to draw it. This is this blue line indicates the observed hydrograph from that data given at point B. This hydrograph was drawn with the help of point B data. Flood hydrograph, hydrograph which enters the reservoir when the elevation is also given, right? So elevation is also given, right? And this orange graph is showing the routed hydrograph. This is the predicted one. This is the outflow hydrograph and a predicted hydrograph with the help of this Goodrich method. So let us come back again to this this sheet or this slide. So you have drawn the distance versus the water level graph. drawn that RHS of equation C versus elevation graph. Now the next time is the solution of the problem. How have you drawn that outflow hydrograph, or how have you predicted that outflow hydrograph? In this Goodrich method, all the thing comes from the continuity equation, average inflow in the time period minus average outflow in this time period is equals to change in storage. S2 minus S1 means here 2 is at the final time, S1 is the initial time, so difference is the storage, change in storage. So from equation A, we rearrange equation A and find equation B. And then what we do? We put all the terms that we know from the known values and initial values of the problem in the left hand side. This is your LHS. And in the RHS, as I have already discussed, this RHS is unknown. And for that graph, we have used we have calculated RHS from that tabular data given in here. Storage with respect to water level and the discharge. Or to be precise, storage, elevation, discharge data. In the first point A, correct? So from that we have find out this RHS of equation C and drawn that graph of the solution step 2. Okay. So next step is what? So to find this 2s2 by del T plus Q to RHS of equation C for the flood hydrograph. Okay. You need to know the terms in the LHS left hand side. You note that from the flood hydrograph you know I1, that is the inflow at the 0th time or the initial time, I2 inflow at the final time. Yes, you have it, you know it already, because that flood hydrograph shows what is the outflow at 0th hour, then after 6th hour what is the outflow, then after 12 hour what is the outflow. So that is for 0 if I take initial and 6 is if I take final. Then for 0 what is the inflow, and for 6th hour what is the inflow, we know it. So add those two inflow, both are known from that given data of point B, correct? Now come plus 2s1 by del T minus Q1. Now this data, what I was saying, this 2s1 minus del T, 2s1 by del T minus Q1 data. Here the problem is that we do not know what is S1. Del T we know, Q1 also we know. Q1 is the outflow at point 1. So Q1 also we don't know. So what we'll do is we have already drawn that graph, right? And we also know from the point C that at initial condition, that means at the 0th time, the elevation is given. And we have drawn these two graphs, step 1 graph and step 2 graph, with the help of the elevation in the x-axis. So from that graph, with respect to the given elevation, what is the outflow, we can derive it. Q at the given elevation, right, from that graph, because the graph is of as I've already shown you. Let me so this is y, this one is y also. One is your outflow and another one is this part RHS of equation C, but from the storage elevation outflow data given at point A. So this is your data del T. So this is your elevation in the x-axis. For both y, elevation is common. So they say that at elevation this, suppose x, the flood start to take place. That is the elevation at t is equal to 0. So from this data, and you have these graphs, right? By drawing a perpendicular into the y-axis from this point, from both the y-axis, you can get what was the corresponding Q outflow for that elevation, and also what was the corresponding 2h2 by del t plus Q2 for that elevation fell. Correct? So after then what we do is, we from equation C, we rearrange it and found equation D. Here what they say? Here they say that to find this value, right, we have to use this value, 2s by del t plus Q minus 2Q2. So for the elevation x, we know what is 2s by del t plus Q, correct? By drawing a perpendicular from that point to the y-axis in Q will give you the outflow, and also a perpendicular drawn from x point to that y-axis, or representing the right hand side of equation C, will give you the corresponding right hand side value, which is this one, 2s by del t plus Q. Correct? So you know this value, and 2Q2, what? Q2 is this, Q at that elevation point x. So this 2Q, okay. So suppose if I draw a perpendicular from x to y-axis, which represent Q, then it will give us Q2, and another perpendicular to that y-axis, which represent the RHS of equation C, will give that RHS of equation C for that x elevation. So indeed, this value is known, this value is known, so this value will be known. Correct? Now put this value into this equation. You know this, find this. And then in the next period, what you will do is, mind it, so you got, I think you understood, from the known elevation I have got Q2, and I have got 2s by del t plus Q from the graph drawn in the first two steps. So by deducting 2Q2 from this RHS data, we have that 2s by del t minus Q data, which is this one, this term of equation C. So from this we get this, and when I add I1 plus I2 with this value, what I get is 2s2 plus 2s2 by del t plus Q2, which was unknown in equation C. Then after that, what happened is very interesting. Then you put this 2s2 by del t plus Q2 here for the next period calculation. And what now? Now it is another interesting part. For this value also, you see, you will find the elevation, because if I draw a perpendicular, suppose this 2s by del t plus Q is this part, so is this part. So if I draw a perpendicular to x upon the elevation, then it will give the corresponding elevation. And the 2s by del t plus Q is known now. So if I drop a perpendicular from 2s by del t plus Q into the x-axis now, then it will give an elevation, corresponding elevation. And if I drop from that corresponding elevation, if I drop another perpendicular to the discharge, then it will give the new discharge for that new elevation. And now it starts to increment. So that new discharge will be this Q2. So then this minus this you get the new this. Then again you put here, add the I1 plus I2 of next time period, you find this one plus Q2. Then find the elevation for this corresponding value from this data graph, and this elevation will also give you that Q2. Then you find it this 2h del T minus Q again, and then again you put it here, again add I1 plus I2, you will find another here. So in this way, for all the inflow discharge of 48 hours, you will get outflow discharge as well as the elevation of the 48-hour time scale. And from that Q, that outflow Q, predicted outflow Q, you can draw the predicted outflow hydrograph, and that is shown here only. This is the actual hydrograph in the inflow, and this orange is the predicted hydrograph at the outflow. You noted that this peak, inflow hydrograph peak, is greater than the outflow hydrograph peak, certainly, because there is resistance in the reservoir, which will reduce the intensity of the flow. So the peak will diminish, and this diminishing of peak from the inflow hydrograph to the peak of outflow hydrograph is known as attenuation. And you see the peak is lagged also. In case of inflow hydrograph, the peak has come here, right? But in case of outflow hydrograph, peak has come after some time T. This T is known as lag. So this is attenuation, the difference of peak in magnitude of inflow and outflow hydrograph, and the time at which the peak has been attained by the inflow and outflow hydrograph. The difference of that time is known as lag. Okay, so this is what is the Goodrick method is. Now in the next slide I will just summarize. Okay, so let us summarize this Goodrick method. It's a very simple method. What you will be given? First you will be given a table of storage, corresponding elevation, corresponding outflow or discharge, correct? So elevation will be in meter, this will be in meter cube per second, and these will be probably in megameter cube, right? So these will be given x1 to xn, y1 to yn, okay. So x1, due to x1, y1 is there, due to y1, z1 is there, okay. This thing I already explained. Now another thing is that the flood hydrograph that is entering to your reservoir will be given. The entire data will be given, the time and the discharge of that flood hydrograph. Some rainfall has occurred in the upstream, or that runoff takes place. At some condition, at some time, that excess rainfall or the excess discharge due to the excess rainfall enters your reservoir. So that time is your 0th hour, and then for every 6 hours the discharge is given. That means inflow to the reservoir is given, correct, and until 48th hour. So this is suppose known as Z1, Z2, Z3, Z4, Z5 and so on to Z48. So you see every time in 6 hours, so del T is known as 6 hours, and this will be converted into second by multiplying 30 into 30. Why we do it? Because this Q is in meter cube per second, so it is better to have this incremental time in second also. So another thing, so this table is given, this flood hydrograph data is given, and third is at what time or at what elevation this flood hydrograph takes place or enters the reservoir, that will also be given. That means elevation at time t is equal to 0 will also be given. Okay, now they will ask, the question will be, draw the hydrograph at the outflow or outlet point. Hydrograph at outlet, let us say. What is that? So the thing is that first step, straight away draw a Q versus elevation curve from this Q data, from this elevation data. Second, draw 2S by del T plus Q versus elevation from this data. 2S by del T plus Q by this table data. 2S del T is given, Q is given. So you can easily draw this data. So two curves is drawn. So the third point or the third step will be, you know that at what elevation the flood has entered the reservoir is given already. Now, I just don't like to repeat. These two graphs of 1 and 2 has a common x-axis, elevation. Here it is Q, here it is 2S del T plus Q, correct? So, you have the elevation data, given elevation at t is equal to 0. What will be the corresponding discharge and what will be the corresponding 2S by del T plus Q? You can easily draw it, because you can easily find it by dropping a perpendicular on the y-axis from the data of elevation, right? If you drop a perpendicular, that is, this is the data of elevation, suppose, drop a perpendicular on this curve of 2S by del T plus Q, and then from this point drop a perpendicular into this axis, so you will get a 2S by del T plus Q for this elevation 1. Similarly, when you extend this line up to this curve, this is the Q versus the elevation curve, and then you drop a perpendicular to here, then you get a Q also. So at that initial elevation, what is the Q and what is this 2S by del T plus Q will be known to you. This is the beginning of the entire process. So you have, when you have this again, when you have this Q and this 2S del T plus Q, so what you will do there is that for this elevation I know what is this, for this elevation I know what is this. So if I, from that equation A, B and C, I can draw this 2S by del T plus 2S by del T, this will not be plus, this will be minus Q and minus 2Q2, right, will be equals to 2S by del T plus Q. Am I correct? I don't think so, because this 2S by del T plus Q, this will be plus and this is minus, okay, will be equals to 2S by del T minus Q, correct? And then what we will do is, with this minus Q we will add I1 plus I2. I1 plus I2 means the 0th discharge, that means this one, plus this one, that means Z1 plus Z2, okay, to this, where it is, to this part, 2S del T minus Q, okay, and this will give you what? this will give you 2s by del t plus q. Now from the graph, again I go to the graph. Okay, so this part you understand, elevation is there, you get elevation. For that initial elevation, what is the q, what is the 2s del t plus q from this graph. Okay, that is I think clear. Now put this value of 2s by del t plus q into this expression and deduct 2q from that. So that will give you your 2s del t minus q. And then what you will do, from in this 2s del t minus q, you add I1 plus I2. I1 plus I2. That will again give you 2s by del t plus q. Now, as you have got this 2s by del t plus q, from this graph again, you see what will happen. 2s by del t plus q, you know, suppose this one is the 2s by del t plus q. Drop a perpendicular, let us, onto the curve and then to the x-axis, that is elevation. Then at that will give another elevation, this new elevation. And this new elevation again, if you extend it towards the q, that distance versus elevation curve, then it will give a new q also. Correct? Is it correct? So then what happens is that, then from that new elevation again, you know, you will get a q and also you get a 2s by del t plus q. So again you have this term 2s by del t plus q minus 2q. This q will be the new q equals to 2s del t minus q. So you have got it again. Then you add the next two, I1 plus I2. So now what happens? These will become I1, these will become I2. So this Z2 and Z3 you add with this new 2s by del t minus q, and you find this 2s del t plus q. Again, you from the graph you get a new elevation. For that new elevation you get a new q and also a new 2s by del t plus q. So put it in the equation, find 2s del t by minus q, right, and add the next time increment inflows I1 plus I2 into this to find this. So this is a rotation goes on until your inflow data for the time increments are stopped. That is when I2 becomes 48, then you stop the iteration procedure. So that is in short is a Goodrick method, and let me show you the. So I have already discussed about the Goodrick method. So you see in this Excel, if you put the elevation data here, okay, if you put the elevation data here, you will get the corresponding 2s by del t plus q data here, and also you will get a new q here. So when you get that, you see the initial time scale, the elevation was 100.6, that was given. Okay, this one was given. So when I put it in here, this is actually this is the given table. This elevation, storage and outflow distance is given as I have told you, and from this data only this 2s by del t plus q is drawn, calculated, and del t is your 6 hours, so it is changed to second, right? And accordingly, so with the help of outflow versus elevation, we have drawn this curve, correct? These I have also already discussed. Elevation versus outflow, and then elevation versus this 2s by del t plus q, and that 2s by del t plus q is also the RHS of that equation C. This is already communicated with you. So So from that we have drawn the graph, and here we use the Excel function of trend function of Excel. Trend function will give you the y value for unknown value of x. If you can provide him the known value of y and known value of x. This is a very common function available in Excel. Just use that trend function with the help of these data only. And then you find this trend data. These are all trend. Okay. So that formula is extended up to this. And then what happens? We know what is the elevation at initial time period. So we put it here. Then and there it gives a new discharge. And also this new 2s by del t plus q data. This I already discussed with you. Then what I do, I come into this table. This is the given data of flood hydrograph, right? Time versus inflow. That I was referring to as Z1, Z2, Z3 for time T1, T2, T3. Okay, in the presentation. So here the formula is I1 plus I2. So I have summed the outflow of initial and final time increment. 0th time, what is the outflow? 6th hour time, what is the outflow? I have had. This was the 0th time outflow. With respect to inflow, with respect to reservoir, it is inflow, but actually it is the outflow or discharge, whatever you say. And this is the final time, what is the, let us say it as inflow. So 10 plus 30, 40 is there. So this is what is, I have got from the trend function 354 for the given elevation data 100.6, and also I have got this discharge data of 15.177. So these two, this one and this one, has been found from the trend function or from the graph when I give the data of elevation. Correct? And then what happens, you see, as I have discussed, from this 354, we have deducted 2 into discharge, 2q. Please remember that slide, last slide. This 354.508 is your 2s by del t plus q, and this is your discharge q. So 2q you deduct, and you will get 2s del t minus q, this one. So from this you minus 2 into this, you will get this. And then you add this 40, that is I1 plus I2, I1 plus I2, and you get 40. And so what happens? You add this 40 with this 324, 40 plus 324, this will be your 364. So this is your 2s del t plus q. So put it into that trend function in this Excel from graph for your case. So what is it? 364. So this is the 364. And then and there it will give me the corresponding discharge, which is 19.271 from the trend function formula. Okay. And also the corresponding new elevation, as I have said. So discharge will be stored for that first time increment as the discharge of the 6th hour, after 6th hour discharge from the outlet of reservoir. So as that discharge, this will be recorded. So now what happens is, from this this new elevation, what will happen? I will get from this new elevation, what will happen? I will get a new RHS 2s del t plus q, from where I will minus 2 into 19 data, correct? And then I will add the 6th hour inflow and 12th hour inflow to that data, and to find this 2s by del T plus Q, correct? So if I add both of them, I am getting a new 2s by del T plus Q data, which will give me a new elevation data, and once I get a new elevation data from the trend function or from the graph, I will get a new discharge and again a new 2s by del T plus Q data. So this is a circular process. It goes on until the 40th hour. Okay, for this actually we have gone up to the 66th hour. So up to 66th hour you get it. So this is the entire process of Goodrich hydrograph, and I have developed this Excel sheet where just putting this given elevation data here, and the given elevation, storage, outflow, discharge data here in this part, and also the flood hydrograph data here in this part. Will automatically give me the predicted hydrograph at the outflow, which I can draw from this data. This data is the predicted outflow hydrograph, which is nothing but this one. This is known as the routed hydrograph. Okay, so this is what it is. I will share this Excel sheet with you. So we close it for now.